So I have a question for you guys, a warm-up question. Which of these, or are these two molecules identical or different? What do you think? They're identical, they're just moved? Are they constitutional isomers? How do we define constitutional isomers? Kind of. Constitutional isomers said they have the same molecular formula, but a different connectivity. Are these connected any different? No. In fact, when you go through the naming worksheet, you'll discover that IUPAC says to find the longest carbon chain. So for example, the one on the left, I'm going to label that one as blue, right? So it's a 5-carbon chain. And then we've got this group coming off of it. Does anybody know what this group is called when it's 1 carbon long? A methyl group. And so using the IUPAC rules that you guys will learn tonight, this will be called 1,2,3-methyl pentane. The pentane means that that parent backbone is 5 carbon longs, and then it's got a methyl group coming off of carbon 3. If we do the same thing for the one over here, it works pretty similar, right? We've got, again, a carbon chain that's 1, 2, 3, 4, 5 carbons long with a methyl group coming off, and the methyl group's coming off of position 3. So again, if we name this, this is 3-methyl pentane. These are identical compounds, right? They're called the exact same thing. Yep? It's one word. Sorry, this looks like there's a space. It should be no space. So it is all one word. So the question is, why did I draw them differently, and does it matter? Do you guys think it matters how we draw them? Yeah, it doesn't matter. I could draw them upside down, sideways. I could spin them around 3 times. They're the same compound, right? These molecules, especially alkanes, are very, very floppy. The question is, why are they so floppy? Sigma bonds, right? If we think about sigma bonds, right? Sigma bonds are that head-on overlap of orbitals. They can rotate and spin freely in space. So this chapter focuses a lot on that unique behavior of alkanes, the fact that they can rotate freely at room temperature. So I'll show you guys how to do some of this conformational analysis. All right, so conformational analysis basically assumes that sigma bonds can rotate. And this is at room temperature. If you cool them down close to absolute 0, the reality is they stop rotating as fast because they don't have enough energy to spin, right? But at room temperature, they're assumed to rotate freely. So another way of thinking about this is, let's imagine this compound. This is ethane. This sigma bond down the center can rotate, and you can spin it around as much as you want. In fact, what I would encourage you guys to do in this chapter is to bring your model kits to class and keep them open while you're working on homework problems so that you can physically rotate the bonds and see how they rotate in space. Helps a lot. So we draw this using a unique system. And first I'll do the 2D one. So ethane is 2 carbons long. We've got a hydrogen sticking up here and down on that other carbon. And then we know that the carbons are sp3 hybridized, so they must be tetrahedral. So we can express their tetrahedral shape using dashes and wedges, right? Alternatively, people will draw it in what's called the Newman projection. And the Newman projection is really not that bad. Students make it a lot worse than it seems. What I do is I always draw a pretend eyeball, and I imagine looking straight down this carbon-carbon bond, right? So let's focus on that front carbon. If we're looking down that bond, we should have 2 hydrogens sticking up, right? Almost like hands. Can you guys see that? And then we should have 1 hydrogen sticking directly down. That's only the front carbon. We're kind of ignoring the back carbon at this point. And then in order to represent that back carbon, what we do is behind that cross, we put a circle. That gives the perspective that that carbon's in the back now. And for that back carbon, we have 2 hydrogens sticking down, so I'll draw those in. And then we have 1 hydrogen sticking up. But do you notice how the lines are attached to the circle? They don't meet in the center. That indicates that those hydrogens are coming off that back carbon, not off of the front carbon. So that's our Newman projection. This gets confusing for students, and if you haven't checked out this guy's website yet, he makes it pretty funny by having a bunch of cat analogies. So he has joke after joke about cats on his website. He says you can draw a cat using line wedge formula where he's got the dashes and wedges. You can draw it with the sawhorse projection, which is the same thing. We've just kind of looked at it, the cat on the side. And then you can do the Newman projection where you're looking straight down the front of the cat, right? It's the same cat, you're just looking at it from different angles. That's really the main difference between line wedge and Newman projections. So if you are kind of stuck on this stuff, his website makes it a little bit more interesting to learn about. My own personal plug for him. All right, so let's try to do some sigma bond rotations. And we'll start with ethane again. So I'll do bond line first. And this time I'm going to color code everything. So if you have colored pens or pencils, it might be a good time to grab them. And I'm going to keep these center carbons the same. I'm going to show my sigma bond network with all black. Whoops. But I'm going to color code my protons this time. Okay, so arbitrarily I'm going to pick red, blue, whoop, green, purple, what should I do? Orange? All right. And then last but not least, I'll do black over here. So now we've color-coded all our protons differently, right? All right, what I want you guys to do now is to imagine that you're looking down this eyeball. And I want you to draw this using the Newman projection. So just like before, we said you always have this cross in the front. So let's focus on that front carbon. Whoop. I'm going to draw this differently. Yeah, it looks kind of like a Y. Why did I draw it that way and not the other way that I had drawn like this? It's the same, right? But if I'm looking down that red line, these 2 protons are sticking up, right? So we should have 2 arms sticking up if we're looking down that way. Okay, so now the question is, does the red proton go on this side, on the right, or on this side, on the left? It's a little bit weird to think about. So imagine you're looking down there. The red proton is a wedge, so it's coming out of the board. So if you're looking this way, it's coming out. So if you look at it this way, it should be going to your right. So sometimes it's a little hard to imagine it that way, but put yourself in the position of the eyeball. Because that's a wedge, it's coming out of the page, and when you flip it on its side, it must be going off to the right. Which means the blue one, if it's going into the board, must be to the left. Can you guys kind of see that? It's a little bit weird to imagine it, but I always think of it this way, right? Red proton's a wedge coming out, blue proton's going in. I transpose it like this, red proton to the right, blue proton to the left. That means that the black proton must be in the downward direction. All right, so now we focus on the back carbon. Back carbon, I fill in that circle. Again, this has 3 prongs coming off of it. Which one's going to be sticking straight up? Green, that one's easy. All right, what about this one to the lower right-hand side? Is that going to be purple or orange? Orange, right? Because it's coming out of the page. When you swing it around and transpose it, it should be in that position. And that leaves us with a purple proton, which must be right here. This is one of the hardest parts of conformational analysis. is getting that three-dimensional view looking down a carbon-carbon single bond. So if you do have model kits, these can be pretty handy. Ethane's a really simple example, but you can imagine if you're looking down a big complicated molecule, it gets pretty crazy pretty quick. So model kits are handy. So let's take a look at what happens when I spin this. So actually I'm going to redraw this down here. So we said we've got a red proton here, we've got a blue proton over, blue proton over here, we've got a black proton going down, and then in the back, we said we have that green proton up, so I'll fill that in. We've got an orange proton to the lower right, and then purple down there. So I've just redrawn the whole molecule again. This time what I want us to do, though, is to only rotate the front carbon. That back carbon is going to stay put, right? Okay? So I'm just going to show the back carbon static, and we're only going to rotate that front one, but let's just do the back one to save time right now. Okay, so in order to do this, what I always imagine doing is I'm going to take this and pull it 60 degrees. I'm going to take this, pull it 60 degrees. I'm going to take this one and pull it 60 degrees that way. So can you guys kind of imagine that front one as a little propeller blade, but we're only doing a half click sort of thing. Okay, so where should the blue proton be if we're showing it that way? It should be overlapping with the green, right? So the way we show this is we can't often show it perfectly overlapped, so we show it slightly offset. Okay? And that means that the one that's slightly offset here on the lower right hand should be what? The red proton. Okay? And then over here, slightly offset with the purple one should be what now? The black one. This compound, or the conformation, I should say, on the left is referred to as staggered conformation. And the one on the right is referred to as eclipsed. And so you can imagine that blue proton, ideally, should be lined up with that green one. The red one should be lined up completely with the orange one, and the black should be lined up completely with the purple. Does that make sense? All right. Now what I want you to do is same sort of thing. We're still only focusing on that front carbon, which has the blue proton, the red proton, and the black proton. And we're going to again pull it 60 degrees back into a staggered conformation. And I want you guys to show the next staggered conformation that would result. So I'll give you guys a minute to draw that one. And I'll give you guys a hint. It's confusing when you're first looking at it, but keep that back carbon entirely the same and then draw in the front carbon. So for example, the back carbon, what's sticking up again? Green. That hasn't changed. What should be to the lower right off that back carbon? Orange. Okay. And then we should have a purple right here. Okay? So if it's going back to staggered, that means that they're not going to be overlapped. They're actually going to be offset like that. Now we have to again determine which colored proton goes where.
How much are we rotating?
Just 60-degree clicks. In fact, I'll write that in the arrows just so we can keep track of it. All right, so what should go in the top right-hand corner? Blue. What should go in the lower corner? Should be red, right? And then what should be in the top left-hand corner? Black. So again, you can rotate these molecules all sorts of directions, but every time you rotate it, you're going from staggered to eclipse back to staggered again. Is it ED or D? That looks weird. Is that right? ED. I'm second guessing myself. Oh no. Staggered and eclipsed? Yeah, and we'll talk about some of the finer details of staggered and eclipsed later on. That's a good question, though. All right, so the way I imagine this is a bit like going through those gates at an amusement park, right? Have you guys seen those? The 3 prongs? You have to go and push it, and then it rotates back. Yeah, turnstile, exactly. So my question for you is, which of these is the highest energy conformation? Which one's the least happy? The eclipse one. Why the eclipse one? Yeah, the electrons are too close to one another. We talked about in Vesper theory that molecules like to adopt their electrons in a shape or orientation so that they're as far apart from one another as possible. When they're eclipsed, you're actually forcing them to be slightly closer to one another, which means that they're a little bit less happy. So eclipse conformation is less stable than your staggered conformations, but you can definitely rotate by it. Those hydrogens are pretty small. They don't rub up against each other very much, and so this can rotate freely in space. So the way I like to imagine this is using a graph, and I'll show you guys how I graph it. So I'll do energy on this axis, and then I'll say rotation over here. Okay, so we said staggered is going to be down here, relatively low in energy. We said up here we're going to have eclipsed. And then the second staggered, is that going to be the same as the first one? Yeah, it's protons. All I did was change the color. So it's going to be down here. So you can imagine it takes a little bit of energy to push it back into that eclipse conformation, but then it drops back down in energy when you go to that staggered conformation. And this can actually continue on indefinitely in either direction. So this can keep on spinning openly in space. It does matter a lot if you start adding in bulkier substituents. So for example, what if we swap out a proton for something like a chlorine, and then another proton for something like an iodine? Do you think it's going to be equal barrier to rotation all the way around? No, you can imagine if we swapped out, let's say we look at this one. I'm just going to pick that orange proton and red proton. If I've swapped out that orange proton for an iodine and that red proton for a chlorine, that next click would involve them rubbing up against one another, and that would have a very high barrier to rotation. So tomorrow when we come in, we're going to be looking at that. If you can, please bring your model kit with you tomorrow and try to practice connecting them and reading through the instructions before class. If you haven't done that already and you're kind of stuck, come talk to me and I can try to help you resolve that. All right, remember on the pod to watch that video. It's only like 10 minutes. It's not too hard, and then complete the activity.